Hello, everyone. Welcome back, and welcome to the more distributed transaction session. And I'm Haibo Chen from Shanghai University. I'm going to chair this session. So we have 3 great talks on distributed transactions. And the first talk will be given by Marcus. He will talk on how to use in distributed balance tree to scale SQL storage for web applications. By the way, as you just see from the slides, VMware, Marcus is currently working in a new research group in VMware, and they're hiring. Okay.
Thank you. Okay, well, thank you very much for coming to my presentation. This is joint work with Josh Leners and Mike Walfish. And the 30-second summary of this work is that Yesquel is a new distributed storage system for web applications that provides the performance, scalability, and low cost of NoSQL, together with full support for the SQL query language. And in order to do that, Yesquel introduces a new architecture for distributed database systems, as well as new distributed data structures to store the contents of tables and indexes. Okay, let's start from the beginning. Web applications such as web stores, social networks, webmail have to store a lot of user data, such as account settings, user preferences, the contents of emails and attachments, posting on the walls, friends lists, and much, much more. And these applications need a storage system on which to keep all this information. And this presentation is about such storage systems. But why should we care? Well, everything in computer science is either about computation, communication, or storage. And it turns out, in the case of web applications, that a storage system largely determines the design of the web application. If you have a storage system that provides a lot of functionality with strong levels of consistency, then the life of the application developer is very easy. If, on the other hand, the storage system provides very little functionality and weak forms of consistency, then the life of the application developer can quickly become a painful nightmare. Okay, back in the late 90s, the premier choice of storage system for web applications was a SQL database system, which provided a lot of functionality and strong forms of consistency. Unfortunately, as web applications started to grow, the SQL database system became a performance and scalability bottleneck. It was too hard or expensive to scale the database system. As a result, about 10 years ago, developers started replacing the SQL database system with what is called NoSQL systems that provided better performance, better scalability, and lower cost than the database system by dropping a lot of functionalities such as transactions, joins, secondary indexes, and so forth. Now, the thing is that these systems lack a lot of features, but they have been evolving over time. And they have, in fact, proliferated like rabbits. And this is what NoSQL system looks like today. This table shows 19 different NoSQL systems, one for each row. And the columns show SQL features that the NoSQL system may or may not provide. You don't have to worry about all the details of this table here, but there are 3 high-level points that I'd like to make here. The first point is that there are a lot of NoSQL systems out there. The table shows 19 of them. In reality, there's more than 100. Yikes. The second point I'd like to make is the fact that the functionality provided by a NoSQL system varies from one system to another. And it's not clear which NoSQL system will suit your needs if you want to build a web application. The third point I wanted to make, and this is not completely evident from the slide here, is the fact that each NoSQL system provides an ad hoc interface, so that if you develop your application for one NoSQL system, and later on you decide to change your mind because the system is no good to a different NoSQL system, well, good luck. The other system has a completely different interface. You have to restructure your application, and that's time-consuming and possibly expensive. Having said that, it is in this context that we introduced Yesquel as a reaction to the NoSQL movement. And the first observation I'd like to make, which is something very simple, perhaps even obvious, is the following. Guess what? NoSQL is not a feature, but rather the absence of a feature. And when you have an entire community which is fixated on not doing something, this is a sign of a problem. This is a sign of confusion. So we asked ourselves, what is it in reality that NoSQL systems are really trying to achieve? And the answer is that they would like to provide a system which is scalable, which is simple and sane to design, to develop, to implement, to maintain, and to operate, but also nimble and cheap to run. And we took those characteristics as the characteristics that we're going to provide in Yesquel. So in a nutshell, Yesquel is a system that provides the advantage of NoSQL key value storage systems, together with full support for the SQL query language. Now, why do we want to provide support for SQL? There are 4 reasons for that. The first reason is that SQL is a declarative language which is very compact. A few lines of SQL code corresponds to pages and pages of NoSQL code. SQL is much more productive. The second reason is that SQL provides a lot of functionality which is useful to develop web applications, such as transactions, secondary indices, joins, aggregations, a rich set of data types, and much, much more. The third reason is that SQL is an industry standard, so that if you develop your application for standard SQL, and later on you want to change your storage system to a different SQL system, you don't have to barely change your application. And finally, the fourth reason is that SQL is universally known. It's standard part of a curriculum of a database course taught in college. So you have a very large developer base who already knows how to code using SQL. Now I'm going to explain you how Yesquel works. But before I do that, let me give you a brief background on the architecture of a database system. A database system has 2 key components. One of them is a query processor, and the second one is a storage engine. You can think of the query processor as being the computation or the active component of the database system. The query processor is responsible for receiving a SQL query, parsing the query to come up with a query execution plan, optimizing the plan, and executing the plan. The storage engine is the passive component or the data component of the database system. It's responsible for storing the contents of tables and indexes. Let me give you an example of how these 2 components interact with each other in order to execute a simple SQL query that selects all the columns from a user's table where the last name matches my friend Mozart's. And here, let's assume, for the sake of efficiency, that there is a secondary index on the last name so that this query can be executed without having to scan the entire table. So this is how it works. First, the query processor receives the query, parses the query, and realizes that, yes, we'd like to select all the columns from the user's table. We have a secondary index on last name. Let's use it. Issues a request to the storage engine saying, please look up last name equals Mozart and tell me the primary key or the row ID that corresponds to Mozart. Gets back the answer. The query processor then realizes, but I don't just want the primary key or the row ID of Mozart, I want all the columns. Issues a second request to the storage engine saying, please return me all the columns that corresponds to this primary key or this row ID. Gets back the answer. Now the system is ready to return the answer to the application. This is everything you need to know about database systems for this presentation. And now I can explain to you how Yesquel works. This shows the architecture of Yesquel. There are 4 clients at the top of the slides inside 4 client hosts. And this is not part of Yesquel. This is the user of Yesquel. And the user of Yesquel is a web application running inside a web server in a data center. This slide shows 4. We have played in our prototype with deployments with up to 96 clients inside 96 client hosts. And the first architectural choice that we made in Yesquel is that each client gets its own query processor, so that as you increase the number of clients, you also increase the number of query processor. You scale the query processing capability of your system with the number of clients. Moreover, because each client has a query processor, the query processor is a user library that links directly to the application so that the client can call the query processor by just making a function call. And this is in contrast to a traditional database system where the database and the query processor run as a separate process, and the client requires inter-process communication to access the query processor, which is much slower than a function call. As I mentioned, the query processor does not keep the contents of tables and indexes. In Yesquel, this is kept in a set of storage servers, which is shown at the bottom of the slide here. There are only 3. In reality, we have played with deployments in our prototype with up to 48 storage servers. Everything is connected by a fast network in a data center. And the second design choice that we made in Yesquel is that we're going to expose the storage servers as a distributed storage system that is responsible for keeping the nodes of trees. And I'm going to talk about trees a little bit later in this presentation, but you can think of that for now as a simple extension to a distributed key value storage system. And the reason we made this choice is because the community already has a lot of knowledge on how to build key value storage systems that are both scalable and fault tolerant by using techniques such as partitioning or sharding for scalability, or primary backup, Paxos replication for fault tolerance. And we are leveraging all this knowledge inside the distributed key value storage system in Yesquel. And between the query processor and the distributed node storage system, we have the storage engine, which also I'm going to talk about a few slides from now. In order to realize this architecture, there are a few design considerations that we have to take into account, which is, first of all, where and how to implement transactions. And the second one is how to implement the storage engine. SQL provides transactions, and so we need to provide transactions somewhere in Yesquel. And in Yesquel, we decided to provide transactions at the lowest layer. This slide shows a logical architecture for Yesquel. The previous slide was a physical architecture. Yesquel has 3 logical layers: a query processor, a storage engine, and the node storage system. And in Yesquel, we decided to provide transactions at the bottom layer, which is the distributed node storage system. Why did we do that? And the reason is because we wanted to take advantage of something called multi-version concurrency control, which is a very efficient form of concurrency control that roughly works by keeping multiple versions of the data. And if you're keeping multiple versions of the data, this is most efficiently and most easily done in the layer that's actually keeping the data itself, which in the case of Yesquel is the lowest layer, the node storage system. How we're going to implement transactions now at the node distributed storage system, I'm not going to go into the details of the protocol, but let me tell you the high-level ideas. The first high-level idea is that we're going to run the commit protocol for transactions directly on clients to avoid additional communication with the coordinator. And in order to do that, you have to remove the power of the coordinator to abort transactions unilaterally. So that transaction is a deterministic outcome of the participant votes, an idea that we take from Sinfonia. The second high-level idea is that, as I mentioned, we're using multi-version concurrency control, which, when you have contention, can be much more efficient than other techniques such as optimistic concurrency control, which is used in some other systems. The third high-level idea is that with multi-version concurrency control, you need to obtain timestamps. And we don't want to incur communication to obtain timestamps. So we'd like to get timestamps from local clocks of processes. However, the local clocks of processes may not always be synchronized. And so we'd like to use timestamps in a safe manner so that even if the clocks are not synchronized, we always satisfy the safety properties of transactions, the ACID properties. And this is a principle that we call clock safety principle. And it makes sense because most of the time, clocks are synchronized inside a data center. And the last thing that we do, the last high-level idea, is that we want to use commutative transactions so that if two transactions modify the same data, they don't have to abort. Now let me talk about Yesquel storage engine. And as I mentioned before, the storage engine is responsible for keeping the contents of tables and indexes, and Yesquel is going to keep that information in what is called order maps. An order map is just a set of key-value pairs where the keys are ordered. And the challenge of implementing the Yesquel storage engine is that you can have a lot of users of the storage engine, and the users of the storage engine are the query processors, and Yesquel can have a large number of query processors. Multiple users modifying the same set of tables at the same time, you have a concurrency control issue here. And so the question is, how do we deal with all these clients without corrupting data and without acquiring too many locks, without coordinating too much? Before I tell you how to implement the order maps, let me give you an example of how we can store a SQL table using the order maps. And this shows a table that has 3 columns. There is a user ID, first name, and last name. And let's suppose, for the sake of this example, that the primary key is the user ID, and there's a secondary index on the last name. This SQL table will get stored as 2 order maps. The first order map maps the primary key to the other columns, and so you can see that 18 gets mapped to Wolfgang Mozart. The second order map maps the secondary index to the primary key. In this case, last name gets mapped to the user ID, and you can see that Mozart gets mapped to 18. Now let's talk about how we're going to implement the order maps. Each one of these order maps is going to be implemented as a distributed balance tree, which is a balance tree whose nodes have been spread over the network, spread over the distributed system. And this is an idea that was first proposed by Boxwood and subsequently improved by Sinfonia and Minuet. And in Yesquel, we improve it even further because we found that the performance of the previous techniques was not sufficient for Yesquel. This shows a balance tree. And this balance tree is used to keep the following order map: A6, D3, G6, J5, and so forth. And the idea of a distributed balance tree is that each one of these nodes is going to be kept in a different storage server. And recall that in Yesquel, we have a distributed storage server for keeping nodes. We're going to use that distributed storage system for storing these nodes. In Yesquel, we made several enhancements to distributed balance trees, the first of which is a better caching mechanism that allows the clients to find the leaf node corresponds to a key in one round trip most of the time without creating contention on the inner nodes of the tree. The second technique is a way to split nodes based on loads. Typically in a balance tree, if a node becomes too large, you split into 2 smaller nodes of equal size each in order to keep a log in depth. But in Yesquel, in addition to doing the splits based on size, we also split based on the amount of load that a node is getting, so that if a node is getting too much load, it gets split into 2 smaller nodes with approximately the same load each. And this is important to get scalability in the presence of skilled workloads. We also delegate splits of the tree to a third party so that 2 clients do not try to split the tree at the same time, which would have created contention. And finally, we have a mechanism to split the tree while other clients are adding keys to a given node. So you can split a node, and another client can be modifying that node. I'm not going to go into the details of these techniques. Once again, these are just the high-level ideas. But instead, let me give you a demo of how Yesquel works in practice. And in this demo, unfortunately, my windows have moved, but there are 3 windows over here. And the window on the left is the interface to Yesquel. It's a SQL query processor. And so in the window on the left, I can type commands to Yesquel. And the 2 windows on the right are the storage servers. There's only 2 here. And I have instrumented the storage servers to print out a status. Whenever it receives a request, it just shows which request it's about to execute so that we can see what's happening. I have pre-populated the database with 2 tables. There's a users table, as I described before. There's also a phones table that for each user has 0 or more phones. So here's the contents of the users table. Select start from users. So this is just a plain SQL. And you can see that the users table has 19 different rows. So there's Bourbaki, Marie Curie, Claude Monet, Spinoza, and so forth. You may be wondering who these people are, and these are people who have decided to give up on NoSQL, and now they have a happy life with their loved ones. And what I have here on the right is that you can see that the SQL command has been mapped into a bunch of read operations, and each read operation retrieves the content of a row. And you can see that this table has been partitioned or sharded across these two different storage servers. Now, let me do a more interesting query here. And in this query, let's just look for the user whose user ID is number 18, let's say. So let's start from users, where UID equals 18. And you can see that we get back our friend Mozart here. And what is more interesting about this query is the fact that the query has been mapped into a single read operation on one of the storage servers. And the read operation is retrieving the row that corresponds to user ID number 18. Now, let me clear this up so that you can see what's going to happen next. In my next query, let's find out the row whose last name corresponds to Mozart, where last name equals Mozart. And the reason this query is different from the previous one is that UID was the primary key of the table. And Mozart is not the primary key, but there is a secondary index on Mozart's. And you can see that this query has resulted in two operations, two read operations. The first operation looks up the secondary index on last name, looking for Mozart, getting back UID number 18. And the second read is just as before, looks up user ID 18 and gets the rest of the rows, or the rest of the columns that corresponds to Mozart's. The last thing I wanted to show in the demo is something slightly more complicated. Let's do a join, where we want to find out all the phone numbers that Mozart has. So to do that, we need to join the users table with the phones table. So select phone from users, join phones on users.uid equals phones.uid, where last name equals Mozart. And you can see that Mozart has two different phone numbers. And this query has resulted in 4 read operations. There's one read operation that looks up the secondary index on the users table to find out Mozart, get back the UID 18. The second read operation looks up on the secondary index in the phones table to find out all the phones that UID number 18 has. And there are 2 more reads, one each to retrieve the 2 phone numbers of Mozart's. This is the demo that I wanted to show you. And the key takeaway here is that you could have implemented these queries if you wanted using NoSQL, if you're using a NoSQL key value storage system, and hopefully this thing is going to come back here. Yeah. But now, if you were to do that, you'd have to manually write the logic that executes the secondary, that looks up the secondary index and gets back the primary key. You'd have to manually write the logic that performs the joins, and you have to manually write the logic that iterates over each one of the answers and feeds that into the application. And this basically amounts to implementing parts of some query processor inside the application for each query and for each application. That's not very convenient. What's more convenient is to have a system like Yesquel that takes a high-level query and automatically maps into a small number of operations on the distributed storage system. So this is what Yesquel is about, and this is what Yesquel does for you. In the remaining time, I'd like to show 2 performance graphs, and the paper has many more. The paper, in fact, has almost 6 pages of evaluation. In the first graph, I'd like to compare the performance of Yesquel with that of Redis. Redis is a NoSQL key value storage system. It's fairly popular. It's used in a lot of websites out there, in Twitter, Pinterest, Craigslist, and so, but by that metric, it's a very successful NoSQL key value storage system. And on this slide, we have compared the performance of read operations executed both in Redis and in Yesquel. The paper has other operations. This is just read operations. And in Redis, we execute a read operation by doing a get on a key. And in Yesquel, we execute a read operation by doing a select star on a table where the key equals k. The x-axis has the number of servers from 1 to 48. The y-axis has the number of reads per second, in thousands of reads per second. And you can see that Redis is always better than Yesquel, but not by very much. Notice that the y scale is logarithmic. In fact, with one server, Redis performs 150,000 reads per second, and Redis is at 127,000, which is worse, but not by too much. And when you go to 48 servers, the performance of Redis and Yesquel scales almost linearly by a factor of 45 or 42. It would have been linearly if the factor were 48, but it's pretty close for both systems. And the last graph I wanted to show you, let me just mention that both of these systems perform with a 99 percentile latency of 1 to 3 milliseconds, which is quite good for web applications. The second graph I wanted to show you is how Yesquel behaves with the SQL query of a real web application, in this case, the Wikipedia. We took the SQL queries that the Wikipedia generates when you search for an article, and we fed those SQL queries into Yesquel, and we measured how many page views per second of Wikipedia Yesquel can serve per second. And these are the results from 1 to 48 servers. And you can see that with one server, we can serve up to 2,300 pages per second, and that number scales by a factor of 41 with 48 servers, which is not perfect scalability, but it's pretty good. Now I'd like to conclude. And before I do that, let me just mention briefly the evaluation summary, the fact that we show through more experiments that are described in the paper that Yesquel performs almost as good as Redis, and that we can scale the SQL queries of a real web application, the Wikipedia. To conclude, I'd like to mention that and recall that Yesquel is a new distributed storage system for web applications that provides the scalability, the performance, and the low cost of NoSQL together with all the features that you get from SQL. So Yesquel basically breaks the belief that SQL is expensive and that NoSQL is required for performance. Now, the last thing that I'd like to say is the following. If you're thinking about a storage system for a web application, don't think about a no, think about a yes, think about Yesquel. Thank you very much.
Hi, Mehul Shah from Amazon. Where do I start? So I got to do this, right? So Amazon has a service called Aurora. It's under the RDS banner and has a similar architecture as your clients or MySQL instances sitting on top of shared storage. Have you had a chance to at least compare against Aurora or any of the other services that you can get fairly cheaply on Amazon? Sorry.
Yeah, I heard about Aurora briefly from you, but I have yet to read a document that describes all the architecture in great detail.
Fair enough. My second question is, your query... You only get one, okay.
Rick Schlichting, AT&T. Have you evaluated this across a wide area when you're doing distribution across wide area?
No, not yet. This is designed for a single data center, but it's interesting to see what would happen across the wide area.
Yeah. Okay, thanks.
Ken Berman. Marcus, this is really cool. So Jim Gray and Dennis Shasha, and I forget who the third person was, wrote this paper on dangers of database replication and argued on paper that you ought to hit a point where contention is causing a high rate of query aborts. So I'm curious to know where their paper was wrong.
Where the paper is what, sorry?
Where their paper was wrong.
Oh, okay. So what we're using here is a technique called multi-version concurrency control that when you have a lot of read-only transactions and you have a small number of transactions that are possibly containing and writing data, then you can do well. Now, if you were to have a very large number of write transactions that are pounding on the same data, then Yesquel wouldn't scale that well. And in fact, I don't know any system that would scale well, because of that. There's also a paper by called, I think, the Dangers of Replication by Jim Gray, which would
That was what I was asking about, yeah.
Yeah, okay, that one. Okay, yeah, no, that one. No, absolutely. I mean, if you have a lot of write contention, you're going to have a scalability bottleneck in the place which is actually dealing with all these writes and trying to resolve these conflicts. And no, there are very few techniques that can get around this. One technique, for example, is commutative operations, and no, we use that to the extent that we can, but not everything is commutative, and so there are always going to be some operations that are writing to stuff that won't be able to scale well.
Great.
Indy Gupta, University of Illinois. Ken stole my question, but I will ask a follow-up. What kind of abort rates do you see in your system, especially when you have a lot of contention?
Yeah, so if you have a lot of read-only transactions, as I said, read-only transactions, you get 0 abort rates. No, you can have one guy writing to stuff and any number of clients reading and you don't get any aborts. Now, as soon as you start getting people pounding on the same data, as I said before, if it's not commutative transactions, then you start getting aborts. And so the answer is really dependent on the workload. And if you have workloads that are extremely contentious, then the abort rates will be fairly high. We have, when we designed the distributed balance trees, and this was one of the drawbacks of the previous work, is that they were modifying nodes in a way that would cause aborts of transactions. And we have spent a lot of time in order to avoid that. But at the end of the day, you always get into operations where you can't use techniques like commutative operations or richer set of data types in order to avoid those things. So I'm not giving a very good answer to your question because really the answer depends on the workload. If you have a lot of contention, then there will be cases in which your abort rates will be close to 100%. And I think that's a fundamental thing that is very hard to avoid.
Okay, thank you. So I'm curious, have you measured the cost of distribution in your system? So have you benchmarked against, say, like a single server Postgres or MariaDB deployment?
Absolutely, yeah, no, we have more results in the paper. We have benchmarked against two things. One is a MySQL system running InnoDB, and that doesn't scale, and we do better than that. Well, if the MySQL system is being accessed remotely, if the MySQL system is being accessed locally, then of course it performs very well.
Yeah, so
we also benchmarked against a MySQL cluster system, where you can scale the number of servers, and we perform by a factor of 5 to 10 better than that.
Sorry, my question is specifically not about scaling. It is about a single machine. So the performance of, say, MySQL versus your system given a single machine. What is the overhead of running your system?
Well, the problem is that if you're designing a web application, you have a data center, you can't have one stored server, which is a single machine. You have a bunch of web servers, and these are all want to access the same data because when you log into the system, you will be placed at any one of the web servers. And so, no, if you could have everything being executed, your web application being executed in a single machine, then that would make sense. But so because that doesn't fit our scenario, we didn't look into that case.
I see, but do you have any numbers on what that overhead is? Just for like smaller applications, might they want to use Yesquel?
Yeah, you're basically asking, no, what would happen if we were to compute performance numbers for a case that is irrelevant to us, and we haven't done that.
Okay, sure, thank you.